Does anyone else need a copy of 4 or 5 notes? I have 2 left. I gave them out last time, if you were here. We didn't start them yet, though. So 4.5. Did you have a copy? Yeah. You know? Okay. So really 4.5 is summarizing everything we've done so far. It's kind of been a little tedious, like, oh, expand the logs, or, you know, move them all to one log, or use addition and subtraction to expand them out. The whole purpose of learning those is to be able to solve exponential and logarithmic equations. So college algebra, we're always looking for what could x possibly be to make the left-hand side equal the right-hand side. So we're going to look at using properties of exponents and logs in applications to solve for the missing values. So the first is solving exponential equations. And the first theorem states, if I have a base to a power equals a base to a power, then the 2 powers have to be equivalent. Right? Okay. So there's 2 ways to approach this. You can take log base b of both sides. If I was to take log base b of both sides, log base b of x equals log, oops, write that better. Log base b of b to the x equals log base b of b to the y. That would give us x equals y. You guys see that? This log base b and this log base b are going to cancel and I get x equals y. Or if you can see it easily enough to write 81 as a power of 3, you can do it that way. The first example, I could know that 3 to the 2x minus 6 would equal 81, but what's 81 in base 3? 4, right? Another way to see that is you could take log base 3 of 3 to the 2x minus 6 equals log base 3 of 81. And you can plug that in your calculator. You can plug in ln of 81 divided by ln of 3, right? That change of base formula we learned last time. Do you need a copy of the 4 or 5 notes, or do you have it from last time? Okay. So you have your calculators. If you're not sure, you can always use log base 3 of both sides. Eventually, we're going to get to where we don't have the same bases, so we have to take log base 10 or natural log of both sides and simplify it from there. So you can always use that process. Log base 3 on the left-hand side, it's going to cancel, and you're going to leave 2x minus 6 equals 4. Add 6 to both sides. And that would give me 2x equals 10, so x would equal 5. Do you guys see that? What about the other a here? Can I write 64 as a power of 4? 3, right? If I wasn't for sure, I could take log base 4 of 4 to the 2x minus 3 equals log base 4 of 64. If I wasn't for sure, right offhand, if I knew what power 4 64 was, I could take ln of 64 divided by ln of 4 and get 3 in my calculator. Do you guys see why I can do that in my calculator? Because it's just a change of base. That's what we learned last time. So log base 4 on the left-hand side is going to simplify to be 2x minus 3. That's going to equal 3. So now if I add 3 to both sides, I end up with 2x equals 6. Divide both sides by 2, and I get x equals 3. So the whole point of the algebra is to get what x equals for the left-hand side of the original equation to equal the right-hand side. They might not always be in the exact same base, but you can always write them. Not always, but sometimes you can write them where we get a base of 5, or in this case, a base of 3. So how could I change 25 to have a base of 5? Where I want to write it as a power. 5 squared, right? So I could write this as 5 squared to the 4 minus t equals 5 to the minus 1, 3t plus 1. So with the same bases of 5, I could then write this as 2 times 4t equals minus 1 times 3t plus 1. Yeah, because this would be to the minus 1 power. 1 over 5 is 5 to the minus 1. That's minus t. What's 4 minus t? Oh, yeah, thank you. 4 minus t, not 4t. This 5 here and this 5. So we can use this property b to the x equals b to the y if x equals y. So I have the same bases, so I know the exponents have to be the same. I could take log base 25 of both sides or log base 1/5 of both sides. You're going to get the same answer. It'll just be in a couple extra steps, and you're going to have to rely on your calculator to simplify it, but you're going to get the same answer as for t. So this ends up with 8 minus 2t equals minus 3t minus 1. So if I add 3t to both sides, subtract 8 from both sides, I get t equals minus 9. So this is just one way to see the same bases. The logs, we can take away from that. We could plug it in our calculator and end up with the same answer. And I'll show you some examples later on where we just take ln of both sides to simplify powers of different bases. If they have the same exponents equal base or equal to each other. But eventually we're going to do an example down here where there's no way to write them as the same base. So I had to take the natural log of both sides. You can definitely take the natural log of the same sides when they do have the same base. It's just a little more tedious, but you're going to get the same answer. As long as you don't do anything mathematically illegal, you're going to be okay. It might just be 4 or 5 extra steps, but as long as you're right, you're right. Which one's the extra steps? The natural log usually? Yeah, when you have the same base, if you can write them as the same base, it might not look like you have the same base, but if you can write it where the bases are the same, you're going to save yourself some work because you're not going to have to worry about logs at all. But if you do use the logs, your answer is not going to be wrong. It's just going to take some more time to get there, which is fine. And we can do it both ways. Sometimes it's some reassurance that I can hit it with a hammer hard enough, I'm going to get the right answer. But if you see it this way, it's going to be faster. Right? Here, I might not have been able to write 81 as a power of 3. I might not have known that. But I could use my calculator and calculate it, and then it comes out to 4. And I have some reassurance there that I use my calculator for that, versus just being able to see, oh, 81 is really 3 to the 4th power, or 64 is really 4 to the cubed. You're not comfortable with that, you can use those properties. So how would I write 27 to be base 3? 3 to the 3rd. So I'm going to write this as 3 cubed. And then I have this 2w plus 5. And then how would I write 1/3? 3 to the minus 1. And that would be 2 minus 5w. So now what it says, exponents are equal to each other. So if I equal to each other, it has 3 times 2w plus 5 equals minus 1 times 2 minus 5w. Parentheses are your friend here because you want to make sure that you're distributing that power to both terms. Right? Because that 3 cubed, that 3 really goes with the 2w and the 5. And the minus 1 goes with 2 and the minus 5w. So I end up with 6w plus 15 equals minus 2 plus 5w. Subtract 5w from both sides, minus 15 from both sides, and that will give me w equals minus 17. So this kind of evaluating exponents, we've only dealt with a specific case when we can get those bases to be the same power. Or we can get those bases to be the same, and then we can set the powers equal to each other. This is kind of leading up to being able to solve for an x. So if I have 7 to the x equals 60, if I take log base 7 of both sides, right? Log base 7 of 7 to the x equals log base 7 of 60. This is going to tell me x equals log base 7 of 60, which I can plug that in my calculator and get 2.1040. That is what x equals. That's the answer. And you can check your work by plugging it into the equation. 7 to the 2.1040 is close to 60. So eventually we want to simplify an expression down to that something to a power equals something. We can take the log of the base of both sides and get that x by itself. Kind of the same setup in Math 040 or 050 or even 110 when I have x plus c equals b. To get x by itself, we subtract c from both sides, right? If I have 10x equals b, to get x by itself, we're going to divide both sides, right? Those are the inverses. So it's the same now if I have 7 to a power equals b. To get that x by itself, I take log base 7 of both sides. And then I can use my calculator to calculate what x is. And I can check my work by plugging it back in. So what would be 5 to the x equals? Yes, very good. So if I take log base 5 of both sides, it's the exact same idea of adding, subtracting, multiplying, dividing, exponents, logarithmic, right? They're inverses of each other. So log base 5 of 5 is going to simplify the left-hand side to just equal x. And the right-hand side is going to be log base 5 of 83. I can plug that in my calculator and get 2.74558. And this is what x equals. I can check that by plugging it into my original equation and show the left-hand side equals the right-hand side. No. I mean, to sure. Yeah, it's just kind of nice to reassure yourself. Eventually with logarithmic equations, you are going to have to check it because the domain for a log equation is only positive numbers, right? So if you get a possible answer to be negative, you have to disregard that. And we'll go over examples with that. But here, exponential, you can plug anything in. If you check it, it just gives you reassurance you did it correctly. So you guys comfortable with the change of base formula? It's ln of the big number divided by ln of the small number. Or you can use log of the big number.
If I don't know how to use mine.
So every calculator might be just a little different. So here's your log button, and here's your natural log. So I could take natural log of 83 divided by natural log of 5, or I could take log of 83 divided by log of 5.
It's the same thing.
It is. It will always be the same ratio.
So you can't like.
Well, you can't type in log base 5 of 83. You have to use that change of base formula. Not that I know of. Or I don't really understand that one. Yeah. So log base 83 divided by log of 5. That's the change of base formula. It's not built into the calculator. You have to do it. Not that I know of on that calculator. So you have your ln and your log. So if you want to evaluate what is log base 5 of 83, you could just put log of 83, right? Oh, so yours just hit it. So if I hit log 83 and then in parentheses, divide by log of 5. In parentheses, enter. And that's going to give you what log base 5 of 83 is. Some calculators you have the ability to change your base, but I don't think that one does. And if it does, I mean, really, it's only one extra step. In your, it's not going to give you any of the algebra. It's just going to give you, can you plug it in your calculator? In some college algebra classes, it would say leave your answer as exact. So log base 5 of 83 would be your answer. Here, I want to know a decimal approximation because there are unlimited amount of ways to write your answer. And we're going to see some of the cases here. There are multiple ways to approach these problems. As long as you don't do anything mathematically illegal, you're going to be able to get to the right answer. Some ways are a little faster than others. But again, as long as you don't do anything wrong, you're going to be okay. Okay. Oh, here? You're a little head. No, that's fine. On A? Yes. Yes.
And take log base 10
yes.
of 49600
yes.
minus 820.
Yes.
And then, okay.
Yes. Yeah. So there's actually two ways you could do it. You could take log base 10 of both sides and then a lot longer process. But yeah, the best thing to do is to get your exponent on one side and everything else on the other. Then you can take your log base 10 or anything really to cancel that and go from here. So yeah, it is going to be. So let's look at this one. The first step we want to do is isolate this term, right? It's the term with the x and it's the exponent term. So one way to do that is to take 820 from both sides. So it's subtract 820 from both sides. This gives me 10 to the 5 plus 2x equals 48,780. Then I really want to get my left-hand side, I want to get rid of that base 10. The easiest way to do that is take log base 10 of 10 to the 5 plus 2x equals log base 10 of 48,720, or 780, thank you. This is just a number. Don't be intimidated by this. It's just a number. Yeah, so what we did here is we got rid of the log base 10 of 10, and we're left with 5 plus 2x equals log base 10 of 48,780. Is it a plus? It's a plus. 5 plus 2x?
It looks like.
Yeah, sorry, the printer sometimes. You can't just zoom in on yours very easy. Maybe 5 more years. 10, 15 at OTC. No, I'm just teasing. No, hopefully no one watches these lectures. Just teasing. Okay, so if we want to solve for x now, this is just a number. We treat it as a number. So subtract 5 from both sides. Divide by 2. This gives me x equals log base 10 of 48,780 minus 5 over 2. If you're careful the way you plug that in your calculator, you should get minus 0.155879102 approximately. Did anyone else get that? You just kept this as a number or in your calculator, then subtract 5 from it and divide it by 2. That's fine. So you change it to a decimal right then. Subtract 5 divided by 2. Yeah, so that's all that number is a number. I might want to hold it until the very end just simply because I don't have to carry out so many decimals. If it says round your answer to 3 decimals or 4 decimals, be a little careful with that, but I could check myself. The log base 10 is 48. Okay, so yeah, you put to a power. That's divided by 2.
Oh.
Yeah, that kind of looks that way. But this is divided by 2. So this is here, not this. So you take log of open parenthesis 48780 close parenthesis minus 5 enter divided by 2. Because if you don't hit enter or if you don't put it all in parentheses, you're really only taking this minus 5 over 2. Order operations in your calculator is important. You could put x equals open parentheses log base 10 48780 minus 5 divided by 2. This is something different than log base 10 48,780 minus 5 over 2. Because if you do it this way, it's only subtracting 5 over 2 versus subtracting 5, then dividing by 2. Did you get it?
Yeah.
Yeah, so just be really careful the way you plug things in your calculator. Sometimes if you just put in the numerator, hit enter, then put in the denominator, you're better off than trying to put it all in one line. Because your calculator is going to do order of operations. So it's going to do this first, and then take this minus this. And that's why I'm going to look at your work and also look at your answer. Your answer you can plug back in to check. 5 plus 2 times that number, take 10 to that power plus 820. Does that give you 49,600? It should. If not, we did something wrong.
Most around, so 100.
Yeah, I'll say probably round to the 3rd decimal or the 4th decimal. But at this point, it's just getting there. And then rounding, if I round 4 decimals, this would be minus 1.559. So what would I want to do on the second part A?
Minus 400.
Yeah, the very first thing I want to do is isolate that 10 to the power. So these are just numbers, so I might as well just put it all on one side. So how would I get that 10 by itself? Log base 10, right? So hopefully at this point I could write this and you guys would be comfortable with it. You guys see that? Then it's just solving for x. 4x equals log base 10 of 62,600, which is just a number. Add 1 and divide by 4. So that's what x equals. Plug that in my calculator. I get 1.44914358. If I rounded that 4 decimals, I would have 1.4491. So be careful with order of operations. The same thing with the previous one. You guys agree with that answer? So
maybe I'm not, I don't think I'm doing my calculator right.
no, you don't put 10 because it's understood it's 10.
Oh.
I mean, you could do log of 62,600 divided by log of 10, but it's going to give you the same as log of 62,600. Right? Dividing by log base 10 of 10 is 1. Your calculator knows what log base 10 is.
Well, I still got 1.1.
Well, this is minus, or this is plus 1 here. You can't add it inside the log separate. This is a number separately. This is a number separately.
See, I still don't get it. Oh, wait.
You could just hit enter. You would on your calculator. So you need to say, what are you taking log of? And then what are you adding to it? And then hit enter from there and then divide by the whole thing.
Okay, I gotta show you what I put because I'm not getting it.
Okay, so you just did the same thing that he did on order of operations here. You just added 1/4. So if you want to do it that way,
It's really not, you have to want to figure out how you want me to do it and then do it.
Okay, so part of it is understanding the calculator and order of operations. Right? So what you did here is you said +1 and then just 1 divided by 4, not the whole thing divided by 4. So if you want,
I think I did. I know.
so if you take log of 6,600 plus 1.
Maybe that's why, but isn't it?
Then divide
Okay.
that by 4.
Oh, okay.
What you did was
Okay,
all of this
yeah, I
plus
thought it
1
would
fourth.
do that, I get it.
Yeah,
Okay,
if you want to put it all in one line, let me know what's the numerator and what's the denominator.
That's what I mean.
So if you want to put it all in one line, you have to say the numerator in parentheses divided by the denominator in parentheses. That will keep everything in order.
Do you not do the +1 though? That,
You do,
you do it.
but you don't put it inside the parentheses. So this parentheses here, +1 is a separate thing, and then divided by 4, if you hit enter, divided by 4, your calculator will know what to do. But if you put just like what I said last time, if you put log base 10 of 62600 plus 1 divided by 4, your calculator is saying 1 divided by 4 plus this, which is different. Your answer is going to be off. You can put your numerator, enter, divided by 4, that's fine. Or you can put open parentheses, your numerator, close parentheses, divided by your denominator in parentheses. In this case, it's 4, so you don't need a parentheses center. Half the battle is solving for x, And the other one is knowing how to input it in your calculator to get the corresponding x. This doesn't tell me much. I don't even know what this number is. This tells me it's about 1.44 or 1.45. If I approximate that here, I can show the left-hand side equals the right-hand side. Questions on that? Let's look at another example here, B's. B's are using natural log, but the one thing you want to remember is you want to get the coefficient to be 1, and you want to get E by itself. So how would I get the coefficient to be 1 here in front of E? Yeah, divide, right? The inverse of multiplication is division. So I'm going to take this and I'm going to divide both sides by 18,000. It just looks scary because this ends up being 1 over 9. E to the minus 0.4t. Now if I do the natural log of both sides, I'm going to get rid of that e. And natural log of 1 over 9 is a number. And I don't have to get caught up on that. It's just a number I'm going to plug in my calculator. So if I take natural log of 1 over 9 equals natural log of e to the negative 0.4t, that cancels that. And I end up with ln of 1/9 equals minus 0.4t. How do I get t by itself? Divide by minus 0.4. This would give me t equals ln of 1/9 divided by minus 0.4. Plug that in my calculator, what do I get? Yeah, keep going. This is what I was talking about. There's unlimited amount of ways to write this, because I could write this as ln of 9 to the minus 1 over minus 0.4. And minus 0.4 can be written as 2 over 5. So I could write this as minus ln of 9 over minus 2 over 5. I could write that as 5 ln of 9 over 2. There's infinite amount of ways to write it, and all of it's going to be mathematically correct. So this is why I want you to round to a decimal, so I don't have to go through all those different variations. And I can just say, oh, they got the right answer. Their work's right. Instead of this is correct, if you take this, it's going to be the same as you plug in this. The same as if you plug in this is the same as if you plug in this. So that's kind of why I want to get to that decimal at the end. So then I can say, yes, your algebra is correct. You didn't make a mistake anywhere. Make sense? If you're wrong, then I'll try to diagnose where your problem went and give you partial credit. So if I can't find anything wrong here, but your answer's wrong, I'm going to give you most of your points. Does that make sense? I want to see the way you work through it, but I also want to be able to grade it relatively easy. What about B? B is the exact same approach. So I have 1/7 equals e to the minus 0.2k. ln of 1/7 equals negative 0.2k. Divide both sides by negative 0.2. So k equals 9.72955.
How many decimal points do you need?
611. No, like 4. I don't know. Probably 4. Oh, no, probably 4. 4 more than 611. No. And honestly, I'm not even too worried about the decimal points. 3 decimal points, 2 decimal points. It's, you know, did you plug in your calculator correctly? Can you get to it simplified where you isolate t, k, x, whatever the variable is? But like I said, I don't want to have to look through all the different ways this can be written. If I can just check, yes, you got the answer right. These next 2 examples are 2 different ways to approach when I have different bases. So there's nothing convenient here where I can take log of the same base on both sides to cancel it. So your process here, I'm going to do A, and then I'll have you guys do B, is to take the natural log of both sides and simplify. ln of 4 is just a number, and ln of 5 is just a number. So you treat it as a number. So if I take ln of 4 to the 2x minus 7 equals ln of 5 to the 3x plus 1, by doing that, that has allowed me to bring the exponents down as coefficients. And I can write this, keep in mind, parentheses will be your friend, 2x minus 7 times ln of 4 equals 3x plus 1 times ln of 5. ln of 4 and ln of 5 is just a number. You can. I would wait until the very end to do that because you're going to solve for x. So now I need to distribute this to both terms. And I have 2x ln of 4 minus 7 ln of 4, which is again just a number, equals 3x ln of 5 plus ln of 5. So it looks kind of ugly, but now we're just adding or subtracting or dividing, depending on, we need to get x by itself. So what terms have an x in it? And 3x ln of 5. So I need to get those on one side. So I have 2x ln of 4. And then if I subtract 3x ln of 5, right? If I move this over here, I need to subtract it. I have ln of 5 on the right-hand side, and I'm going to move this to the right-hand side. So I have plus 7 ln of 4. So you see what I did there? I added or subtracted the terms I wanted on the left-hand side and on the right-hand side. And I want the terms with an x in it on the left-hand side. Doesn't matter which side you put them on. This term has an x in it, so I leave it here. This term doesn't, so I add it to the other side. I'm adding it to both sides, but it cancels here, right? I want to get this 3x ln of 5 on the left-hand side, so I subtract it from both sides. And I get that term. Then if I was to distribute out an x, what would I be left with? Very good. 2 ln of 4 minus 3 ln of 5 equals ln of 5 plus 7 ln of 4. And the last step is to get x by itself, is divide both sides by 2 ln of 4 minus 3 ln of 5. So x would equal ln of 5 So this is what x ends up equaling. That is the answer. Put that in your calculator. Be careful if you want to put it all in one line. make sure you would put this in parentheses in your numerator and this in parentheses in your denominator. But if I do that, I get minus 5.50341. So convince yourself ln of 5 plus 7 ln of 4 divided by 2 ln of 4 minus 3 ln of 5 is minus 5.50341.
So with that, E's, we give you that ending.
The A and B E's is set up a little differently because there's E and E squared, or E to the 2x. You have to do a U substitution there. Didn't get it? Drawing calculators will do all the time. ln of 5 plus 7 ln of 4, right? Divided by the same thing. They're all in one. So if I hit here, I'm going to insert, I'm going to hit here. So all this is going to be in the numerator. Divided by everything in the denominator. And then go along with it. ln of 5 plus 7 ln of 4 divided by ln of 4 minus 3 ln of 5. So if you're going to put it all in one line, you need to put your numerator divided by your denominator. So yeah, parentheses are your friend if you're going to use your calculator, and all in one line. You can put the numerator in, the denominator in, and then plug the numerator divided by the denominator, but that's honestly, I think, more likely to make a mistake than if you just put in one, if you do it correctly. And you should confirm doing that. Did you guys figure it out? Get the same answer? If you do it, and you just have to be what you're comfortable with. So if you take ln of 5 inner plus 7 times ln of 4 inner, and then write that number down, take 2 ln of 4 inner minus 3 ln of 5 inner, write that number down, and then take the top number divided by the bottom number, that's fine. So B's around the same approach. I'm going to let you guys work on B on both of these. I want to go over this last type. And then on Monday, I'll go over the answers to both of those. So this setup is different because I can't get E by itself, right? I can't get E on one side by itself because there's an E squared and an E. So if you see a problem like this, this is a U substitution problem where I'm going to come in here and I'm going to let U equal E to the X. So U squared would be E to the X squared, which would be E to the 2X.
Yeah, where's that U come from?
This is the process. This is the technique to solve this type of equation. It's called a U substitution. So I can't solve this by itself, but what this is an X. This is a quadratic in E to the X. So first we need to say, what is it in terms of U? So this would be U squared plus 5U minus 36 equals 0. You solve this quadratic. So what would be the factors here?
6 and 1.
4 and 9? No, that's fine. You were just going through. Yeah, so here, this would be U would equal 4 or U would equal minus 9, right? If this was in U, these would be the answers, but it's not in U, it's in E to the X. So you would say E to the X equals 4 or e to the x equals minus 9. So here, this would be x equals ln of 4 or x equals ln of minus 9. Can I take ln of minus 9? No, this doesn't exist. Does not exist. So my answer would be ln of 4, which I didn't plug that one in my calculator. So the process, when you see something like this, is to make it a quadratic. U is a general technique for a U substitution. Basically, we're just subbing it in to solve for it, and then we're back subbing it. So we can call it U. You can call it anything you want. You can make them X's. The key thing here is to solve for the X at the end.
So,
But I don't understand what the point of it is, though.
So this is a quad. Yeah.
I mean, if you just left it at E and did the exact same thing, wouldn't it? You know?
So the variable here is in the exponent, so it's not a
So
true
it just
quadratic.
is,
A quadratic would be something. So I can write this. Really, what I can do, it just makes it a little simple. What I'm doing here is this e to the x squared plus 5e to the x minus 36 equals 0. So this e to the x is my variable. I'm solving for what variable. Sometimes it gets more
That's why I
complicated
just think it's weird.
seeing it this way. And that's why if we let it be u, we see it exactly like we do in Math 110. We can solve it from Math 110 and then back substitute it for e to the x equaling that. But yeah, you're right. This is a quadratic, but instead of our variable being x, our variable is e to the x. So once we solve for our variable, we set e to the x equal to that. In Math 110, you would just say x equals 4, x equals minus 1. But in this one, it's e to the x equals 4, or e to the x equals minus 9. This can't happen, though, so we disregard it. It's called an extraneous solution. So I know I kind of hit you hard with some of these. We will go to solving logs, and this is the exact same approach. We have one extra step because we have to make sure our solution exists. Because an exponential, I can plug anything in there. X to any number or b to any x number is going to exist. But for a log, I cannot plug in negative numbers. So I need to make sure if I got here x to be -1, that's not going to work because I have a problem. So we'll go over this on Monday. I want you guys to work these two at home or on Friday, and I will see you guys in class on Monday. This is where we'll kind of start. It's the exact same process. We don't have class on Friday. So